Hi, this is Chris Young. Welcome back to episode 60 of Contemplating Life. We took a couple of weeks off after the Oscar episodes, and we're ready to get back to my stories of my nostalgic look back at my college days. We're going to continue with my fourth semester at IUPUI and the first paid programming jobs I ever had. My transcript for the spring semester of 1975 shows that I took psychology as a biological science, Psych 105, which I discussed in the previous episode. I earned a B for that class. Next I had Physics 152, Mechanics, which I've also talked about in other episodes, especially the one about my friend Mike Gregory, who took the class with me. That was another B for 4 credit hours. I also had Math 261, Multivariate Calculus, which was my first calculus class ever. I never was very good at calculus or differential equations, but I managed to sneak through with a C. Finally, we get to my second ever programming class, Assembly Language Programming, CS 300. It was very frustrating that this was my fourth semester trying to earn a BS degree in computer science, and I was just now getting to the second class in my major. I explained previously that they had mistakenly identified me as a math major rather than a computer science major, and that got me off sequence. Let's talk for a little bit about what we mean by assembly language programming. I'm going to get a bit technical for a minute or two, but I'm going to try to explain some programming concepts in layman's terms. Now, there are a variety of ways to program a computer. Computers don't understand English-like languages or algebraic formulas to do calculations. So most of the time we write programs in what's called a higher-level language. My previous programming class, CS 220, taught programming in the now obsolete language called Fortran 4. Suppose you wanted to calculate the area of a rectangle. In Fortran, you might have commands such as width equals 5, height equals 7, area equals width times height, or you use an asterisk as the symbol for multiplication. That's a very simple formula, but you could have much longer calculations all in one statement. For example, the volume of a sphere might be radius equals 5, volume equals 4/3, asterisk pi, asterisk radius, asterisk radius, asterisk radius, because the volume of a sphere is 4/3 pi times the radius cubed. Now, computers cannot understand any of this directly. You have to use a specialized program called a compiler that translates a high-level language like Fortran into something called machine language. A machine language is nothing but a series of numbers that the computer interprets as commands to do various things. Computers have a section of circuitry called the Arithmetic Logic Unit, or ALU. The ALU consists of some registers to store temporary numbers. Some commands load data from computer memory into a register. There it can be added, subtracted, multiplied, or divided by a number in a different register, or perhaps by a number stored in memory. Once the number is in a register, you can also compare it to a number in a different register. Based on how that comparison went, you can conditionally jump to a different part of the program. Or you can remember where you were, jump to something called a subroutine, and then when the subroutine is finished, you jump back to where you left off. There's a special register called the program counter, which points to the next instruction in memory to be executed. When it completes that command, it increments the counter to the next instruction. The program instructions and the data it works on are all stored in the same memory. If you're not careful, you could jump to a location that contains data rather than instructions. The computer will try to interpret that data as an instruction to do something, when it really wasn't meant to be. The program can go haywire, doing God knows what. The machine language consists solely of binary numbers That is a series of ones and zeros. And it's hard for humans to read. Now we can group the zeros and ones into groups of 4 into base 16 numbers, also known as hexadecimal numbers. But that still doesn't tell you what the instruction does, unless you can memorize the codes. For example, 3C1267 means you should take the value at memory location 6712 and load it into register A. By the way, that's not a mistake. The lower order 2 digits of the address go first. So you specify it 1267, but it really means address 6712. Now, assembly language, which is what we're studying in CS300, is one step above machine language. In machine language, the previous command we talked about would be LDA my value. The command LDA means you're going to load something into register A. And that's relatively easy to remember that LDA means load register A. But where are we going to get what we want to load? Well, we could remember that there's a memory address, like 6712, but it's easier if we just make up a name for that location. In this case, we call that location my value. A program called an assembler translates that command into machine language. Assembly language is just a human-readable form of machine language. Somewhere in the program prior to this, you had to tell the assembler to set aside a memory location that would be used in the future and to refer to it as my value. The assembler sets up something called a symbol table, so you don't have to deal with numbered locations. You just refer to it by the name that you made up. You don't have to remember it was location 6712, and you don't have to remember the opcode for loading a register was the hexadecimal value 3C. The assembler takes care of all that for you. So there's a one-to-one correspondence between assembly language and machine language. Every time you write an assembly language line of code, the assembler translates it into a single machine language instruction. The advantage of assembly language is that you're talking to the computer in its native language, and you can make the code run very efficiently because you're telling it exactly what to do in exactly what order. When you program in a high-level language like Fortran, you're counting on the compiler to translate what you wrote in Fortran into something efficient in machine language. The advantage of high-level languages is they're easy for humans to read and write. The disadvantage is they might produce a sequence of commands that's not fully optimized. Well, at least in theory. Today's compilers can probably optimize their code better than most programmers can. This is especially true now that computer processors have multiple cores that can execute multiple threads of instructions simultaneously. Modern compilers can figure out how to do that efficiently. Back in the early 70s, people still used assembly language when they wanted the most efficient code. Sometimes today, you might still use assembly language if you're concerned about code that ran with exact timing because of hardware constraints. But these days, people very rarely write assembly code. Even though assembly language commands tried to use mnemonic codes that were allegedly easy for humans to remember, like LDA means load into register A, there were hundreds of commands with different variations, and we never could keep track of them all. We had something called an IBM System 360 reference card. It was a fan-folded card about 8 inches tall, maybe 3 inches wide, with 4 panels printed front and back on green cardstock. I included an image of one in the YouTube version of the podcast. I found a PDF of it online. Somewhere along the way, the campus bookstore quit selling the famous little green card. They replaced it with a version for the IBM System 370 that was printed on white cardstock. One day someone said, "Can I borrow your little green card?" And the sarcastic reply was, "They don't make little green cards anymore." So we grabbed a white card and wrote across the top of it, "This is a little green card." So even though they were white, we still called them their little green cards. These quick reference cards were very valuable tools. Years later, I met a guy named Paul Nanos. We were both members of the Speedway Radio Shack Computer Users Club. Paul created a series of quick reference cards for a variety of personal computers, and I even helped him write one for the Timex Sinclair 1000 computer. I sold the quick reference cards through my business, although I never made much money from them. But that's a story for another day. By the way, in the examples I gave above, I'm using codes for the Intel 8080 processor used in early personal computers, even though that CS300 class I took was for the IBM 360. See, that's another problem. Every type of hardware has its own unique set of machine instructions. It has a different set of registers and different commands for how to move numbers in and out of those registers and how to manipulate them. So assembly language written for an IBM 360 that we had at IUPUI would not run on the digital equipment DEC System 10 that we also had. Nor would it run on the IBM 1620 computer that we had. None of those assembly languages would work on the new Intel 8080 or Zilog 80 or MOS Technology 6502 processors that were used in early personal computers. However, if you wrote a program in Fortran and you had a Fortran compiler on your IBM 360 or your DEC 10 or your Radio Shack Model 1 or your Apple II, it would compile your Fortran program into the machine language of your particular machine. And as long as you didn't try to use any hardware-specific or operating-specific features, it would work. When using machine language or assembly language, a program written for one type of computer will do nothing on a different kind of computer. A program intended to run on an Intel-based processor in machine language running on Windows would do absolutely nothing on your iPhone, which uses a completely different kind of processor. That's what bothers me about sci-fi stories, where we hack into an alien computer, or they're able to hack into ours and upload viruses. Probably the worst offender was the 1996 film Independence Day. Jeff Goldblum was able to hack in to the alien computer and upload a virus to disable the shields. If I gave you a memory dump of a program written for an IBM 360, unless you understood the internal workings of the machine and the exact function of every operational code, there's no way you could tell what the program did, and there's no way you could write a program for that machine without that basic knowledge. When looking at a dump of the computer memory, there's no way you could tell which numbers were program codes and which numbers were data that the program operated upon. Machine language programs are nothing but strings of numbers in memory. There's nothing inherent about them that tells you it's from an old IBM 360 or an old Intel 8080 or a modern Intel CPU. Well, perhaps if you understood machine language for those types of machines, you could try to reverse engineer it and see if it corresponded to machine language instructions for one of those machines. However, if it was alien hardware, you had no idea of the internal workings of those computers. You wouldn't be able to make heads or tails out of it, let alone write a program that would run on their hardware. Anytime you see someone in a movie look at a string of numbers and suddenly declare, "It's an algorithm, and it does whatever," that's nothing but BS. I've seen it in a number of movies and TV shows. The worst offender of this scenario is the Star Trek Next Generation Season 6, Episode 20, The Chase. Captain Picard reunites with an old friend who's an archaeologist. Professor Galen is killed by pirates who are trying to steal information from him. Picard discovers that the professor is collecting a series of numbers, but they have difficulty deciphering the pattern. They finally realized that the numbers correspond to sequences of DNA that had been found on planets all over the galaxy. They also determined that there's a secret message in the DNA. Now, technically, there's nothing scientifically impossible about that. We can already produce DNA strands of a particular sequence, and it's not impossible to think that you could encode a message in some creature's DNA. The problem comes when Lieutenant LaForge suddenly declares there's more to this DNA than appears.
This is not part of a natural design, Captain. This is part of an algorithm, coded at the molecular level.
An algorithm? Are you saying that these DNA fragments are elements in some kind of computer program?
I know how it sounds, but there's no way this could be a random formation. This is definitely part of a program.
That's just ridiculous. So we got a string of numbers, and they're encoded in DNA, and we link them up to get a certain pattern. But there's no way to know that that string of numbers is actually a computer program. Because the way you turn numbers into programs is totally dependent upon what kind of hardware you're using. The numbers 3C and hexadecimal means load into register A on an Intel 8080, but that same number could mean anything on a different kind of computer. The string of numbers that represents a program on one machine would be nothing but random noise for a different type of computer processor. And whoever it is that encoded this message into the DNA, allegedly billions of years ago, would have no idea what kind of hardware we're using today. Later on in the episode, when they finally connect all the pieces of DNA, somehow their tricorder device magically starts running the program and projecting a hologram of the recorded message. First of all, the idea that this program could magically reconfigure the tricorder to project a hologram, which is nothing we've ever seen that device do before, and then somehow decode the video and audio and project it in a 3D hologram, is totally ridiculous. But we'll give him that one. The message is 2 minutes and 10 seconds long. I timed it. I downloaded the episode, I clipped out that 2 minute, 10 second scene, and it was over 68 megabytes long. That must have been some lengthy sequence of DNA, much longer than what was depicted in the episode. There are also those stories where someone creates a computer virus, and the simple act of looking at the file causes your computer to get infected. That's a load of crap as well. Probably the worst offender in this category was the Dan Brown 1996 novel Digital Fortress. There was a computer virus that was so dangerous they couldn't open it to see what was inside it. That's ridiculous. A computer file is nothing but a string of numbers. If those numbers are in the proper form, and you name the file as something.txt, then you assume it's a text file. You could open it using your Notepad application, and it would either have plain text in it, or it would come up as garbage. But opening the file with Notepad, when it thinks it's a text file, is not going to infect your computer. If it had an extension like .docx, then maybe it's a Microsoft Word document file. And if you use Microsoft Word to open the file, there might be some macro codes or program extensions embedded in it. And that could possibly be dangerous, but it's only because Microsoft Word allows you to embed programs in what should otherwise be a text file. The most dangerous type of file is one with the extension .exe, which means executable. If you try to open that file, your operating system will execute it as if it's a program. But all you have to do to safely examine the file is to rename it to something like whatever.dat, which means it's nothing but a data file. Then you get a program that can safely open that file. It doesn't try to execute any code, but it just looks at the string of numbers inside the file and displays them for you. That's 100% safe. The only way that a file can infect your computer is if you load the file into memory and somehow cause your program counter to start executing that file like a program. So you don't need anything special to look at a file safely. You don't need antivirus programs. You don't need to have an air-gap machine, which means a machine that's not connected to the internet. Computer programs are just strings of numbers that are no different than data. It's only what you do with those numbers. So anyway, time to get off my soapbox and get back to my story. When I got my first personal computer, using a Zilog Z80 processor, I did have to write some assembly language. Sometimes I had to translate that assembly language into machine language myself because I didn't have a suitable assembler program. One time I taught a class in Z80 assembly language for members of that Radio Shack computer club I talked about earlier. The concepts I learned while writing IBM 360 assembly carried forward when I had to write assembly language for other types of hardware, even though those languages were different. But for the most part, I never had any practical use for IBM 360 assembly language programming that I learned in CS300. Well, I said for the most part, because although I never had legitimate use for IBM assembly, my first paid programming job was writing IBM assembly language, illegitimately. I think it was perhaps my third year at IUPUI, and a computer technology student came up to me and asked me if I would write some programs for her. She had to write about 15 very simple programs in IBM 360 assembly. It was one of those situations where she had all semester to write these programs, but she waited until the last minute to do it. Well, I was sympathetic towards her. I had been through that same scenario. I'll tell you about that in a later episode. Anyway, she needed to write about 15 programs in 10 days. She says, I can write all these programs. I just don't have time to do it by the end of the semester. Look at this list, pick 4 or 5 of them, and I'll pay you $20 per program. I picked out 4 of what I thought were the easiest assignments and told her I would do them. I started out by writing the programs in Fortran, but I did it in a very primitive kind of way. I pretended I was writing assembly language, so I used very simple Fortran commands. I made sure that the program ran and produced the proper results. I could run that Fortran on the DEC 10 computer sitting at a computer terminal. If the program didn't run properly, I could edit the file and rerun it a dozen times in just a few minutes. But running programs on the IBM 360 was much more difficult. You had to type the program onto punch cards using a key punch machine. You then submit the deck of cards to the computer operator, and he or she would put them in a pile and run them in the order they were received. Then you had to come back in a half hour or so, pick up your output, and if it didn't work, then retype some of the cards and resubmit them. That's why the woman couldn't get all those programs done in a short amount of time. By getting the basic logic of the program working in Fortran and working out all the bugs quickly, and then rewriting it in assembly language, I think I got all 4 programs working the very first time I submitted them. She paid me in brand new, crisp $20 bills, fresh out of an ATM. I used the $80 to buy a fancy new HP 21 scientific pocket calculator. I think it cost about $125, but that $80 got me most of the way there. Now, I know I shouldn't admit that I helped someone cheat by doing their homework for them, but I looked at the other code she wrote. I'm confident she was correct when she said she could have written all of them if she had the time. Now, my first legitimate programming job was also in assembly language, but it wasn't for the IBM 360. It was for the Intel 4040. The 4040 was a slightly more advanced version of the Intel 4004, which is widely considered to be the world's first microprocessor. It was a 4-bit computer. Compare that with computers today that are 64 bits. It wasn't good for much of anything, but the way the computer architecture was designed, it was obvious it was intended to be used to create the calculator. I don't remember all the hardware details. It was very primitive in that it would only add and subtract, but could not multiply or divide. Now, binary multiplication is pretty easy. You just shift the bits to the left and add them repeatedly. There was a guy who was an electrical engineer who was a friend of a friend. I don't remember the guy's name. I don't remember the friend's name. But anyway, this guy needed someone to write about 30 or 40 lines of Intel 4040 code for a digital thermometer. All it had to do was read in 6 bits of data from an input port, do some addition and multiplication on it, and store the result in a particular location. He gave me some photocopies of the hardware manuals for the 4004 and 4040 processor. I had to teach myself 4040 assembly language, write the program, and then hand translate it into hexadecimal code, because we didn't have an assembler. Along the way, I learned a little bit about digital electronics. For example, the input command read data from a pair of 4-bit ports, making a total 8-bit value. But we only needed 6 of the bits. I assumed that those top 2 bits that we were not going to use would default to 0, but they don't. A disconnected pin on the input port of a microprocessor, in all likelihood, defaults to a 1 rather than a 0. So you have to mask off only the bits that you want. This was the lesson I would use regularly decades later when I began programming Arduino-based microprocessors. I never dreamed that someday I would be programming a computer smaller than a deck of cards that had similar computing power to my first PC, which was the size of a microwave oven, and that the programming skills I learned on that simple little digital temperature sensor would be essential to the microprocessor programming I would do much later in life. Anyway, I wrote the program out in Intel 4040 assembly language on a yellow legal pad. To the left of each assembly language instruction, I wrote the hexadecimal codes that I hand translated into machine language. To the right of the commands, I wrote comments that explained step by step what the program was doing. The guy paid me $100 and was quite grateful. He said if he ever needed another piece of code written, he'd be happy to hire me, but he never did. This was my first legitimate job as a computer programmer, and I have fond memories of the experience. I spent that money on a more advanced HP 25 scientific pocket calculator that was programmable. I've got a funny story about that gadget for another episode. With the exception of everything I described above, I had absolutely no use for what I learned in CS300 assembly language programming. I earned 3 credits, and it was the easy A. I don't even remember who taught the class. I think it might have been Professor Rizzo, but I'm not sure. However, there was a more significant after effect of that class. It's had a major impact on my life ever since then. It was in that CS300 class that I met a guy named Rich Logan. You've heard me talk about him previously because he and his wife Kathy have been very loyal friends ever since our college days. They frequently take me to movies and occasional sporting events, and have been the best friends that anyone could ever hope to have. We will talk more about them and some other friends I made about that time at IUPUI in next week's episode. It may be a difficult episode to write. I've talked about a lot of other people I went to school with, in grade school, high school, and other college friends, but most of them are long gone from my life. We either drifted apart, like my old girlfriend Ellie or my buddy Dennis, who I still keep in touch with, but we're not really close. Or some of them have sadly passed away, like my girlfriend Rosie or my good buddy Mike. But Rich and Kathy are still a very big part of my life 48 years later. I'm not going to be able to tell their entire story in just 1 or 2 episodes, but we'll hit some of the highlights of the early part of our friendship next time around. I'd like to dedicate this episode to my good friend and caregiver Brandon Drake, who tragically passed away from an epileptic seizure on March 9th. You were a good friend and a great caregiver, and I'll miss you always, buddy. Rest in peace, my friend. If you find this podcast educational, entertaining, enlightening, or even inspiring, consider sponsoring me on Patreon for just $5 a month. You'll get early access to the podcast and other exclusive content. Although I have some financial struggles, I'm not in this for the money, but every little bit helps. As always, my deepest thanks to my financial supporters. That means more to me than words could ever express. And even if you cannot provide financial support, please post links and share the podcast on social media so I can grow my audience. I just want more people to hear my stories. All of my back episodes are available, and I encourage you to check them out if you're new to the podcast. If you have any comments, questions, or other feedback, please feel free to comment on any of the platforms where you found this podcast. I will see you next week as we continue contemplating life. Until then, fly safe, everyone.